Hello everyone and welcome. First and foremost, I want to thank everybody for joining today's webinar. Today I'm going to discuss different evaporation technologies and how they correlate to different applications. I'm going to first start off with an overview of evaporation, then get into three evaporation technologies, which are benchtop evaporation, which is also known as rotary evaporation, industrial evaporation, and then parallel evaporation. At this point, I'm going to summarize everything up, and then at the end, we'll have a session for questions. If you have a question during the webinar, please submit it. I'll get to all questions at the end of the webinar, and if there's a chance I don't get to every question, my contact information will be on the last slide. Just email me or call me, and I can get your question answered. Okay, so what is evaporation? Evaporation is a transformation of a liquid into vapor form. This is usually followed by a condensation step, which transfers the vapor back to liquid form. This overall process is known as distillation. To perform the evaporation step, you need an energy applied into the system, and this has to be in the form of some type of heat. To perform the condensation step, you need an energy applied out of the system, and this needs to be in some form of cooling. You need these two energies, the energy in and the energy out of the system, to be equal to one another to have an efficient overall distillation process. And in a couple slides, I'll explain how you can have your most efficient distillation process. So when you're evaporating, it's always paramount, very important to evaporate under vacuum. This is because the boiling point of a solvent is strictly dependent of the pressure in the system. It follows the Clausius-Clapeyron equation. Pretty much what it does is you're pretty much manipulating the boiling point of a solvent by reducing the pressure of a system. This is advantageous for two reasons. One, you're going to protect thermosensitive samples. For example, let's say you're evaporating water, which has a boiling point of 100 degrees Celsius. If you apply pressure to the system, you can actually evaporate water at temperatures as low as 40 degrees Celsius. So you're going to keep those compounds protected at a very low temperature. And then second, obviously, you're going to speed up the evaporation process. So anytime I talk about evaporating under vacuum, I have to mention the change in 20 degrees Celsius rule. This rule was created here at Buki, and it's very important to always apply this rule when you're performing your evaporation step because it's going to give you the most efficient overall distillation process. So what the change to 20 degrees Celsius rule is, it's pretty much saying that the speed of evaporation must be attuned with the vacuum and the coolant setting. So pretty much any time during the evaporation process, the vapor temperature needs to be about 20 degrees Celsius higher than the coolant temperature. And this next slide will make more sense here. You can see that we have three different temperature zones, T1, T2, and T3. T1 is your actual water bath temperature. T2 is your vapor temperature. And then T3 is a coolant temperature. So let's say you're using a water bath temperature of approximately 60 degrees Celsius. Your job as a user is to fine-tune that vacuum setting so that the pressure, or so that the vapor temperature is approximately 20 degrees less than that. So it should be about 40 degrees Celsius. And then to efficiently condense these vapors, you need the coolant temperature to be approximately 20 degrees less than the vapor temperature, so it should be about roughly 20 degrees Celsius. So let's go over another example. Let's say you're using a water bath temperature of 50 degrees Celsius. So what you do is fine-tune that vacuum setting so that the vapor temperature is approximately 30 degrees Celsius. And then make sure you're using a coolant temperature of approximately 10 degrees Celsius. Now, it doesn't have to be exactly 10 degrees Celsius. It can be under 10 degrees Celsius on the cooling, but you just don't want it higher than 10 degrees Celsius because what will happen is you'll actually stack that condenser with vapors, and you'll actually end up pulling vapors into the vacuum pump, and then that's going to create emissions in your laboratory, and no one wants that. So that's the overall change in 20 degrees Celsius rule. Again, make sure you always follow that when you're when you're performing an overall distillation process. Okay, let's get into rotary evaporation. What I have shown here is an all-in-one rotary evaporator. And what an all-in-one rotary evaporator is that all the components that make up a rotary evaporator are controlled by one interface, which is the vacuum controller. So you have your water bath shown there, which remember, that's the energy applied into the system, and that's going to come in the form of heat. You have your primary condenser, which is the energy out of the system, which is the coolant going through the coils. That's going to be produced by the recirculating chiller. You have your vacuum source, your vacuum controller, and your job with this is to, again, always make sure that the vapor temperature is 20 degrees less than the water bath temperature. Then, obviously, you have your evaporating flask where the sample is held in liquid form, and you have your receiving flask where the vapors are condensed back into the receiving flask back to liquid form. If you have a chance to use an all-in-one rotary evaporator, do it. Again, you're going to see a more efficient distillation process. When you can control all the components with one controller, you're going to save energy, it's more safe, and it's easier to perform these evaporations with this. So if you can, please do so. So what are the reasons why you would want to go with a benchtop rotary evaporator? Well, the main reason is because you're working with medium sample volumes. So a benchtop rotary evaporator can fit sample volumes up to 5 liters. I want to address this now because I get asked this quite a bit. So if you're working with a 5-liter evaporating flask, your sample volume should be half that evaporating flask, the maximum. So you should be about 2.5 to 3 liters. Also, a common reason to choose a rotary evaporator is simple removal of a solvent mixture, which is acetonitrile and water. Let's say you're just stripping off the acetonitrile, a rotary evaporator is great for that. Also, the condenser flexibility. Let's say you're working with low or high boiling point solvents. You actually have the capability of condensing these solvents with either choices. So if you're evaporating a low boiling point solvent, you would use a cold trap condenser. That way you can actually put dry ice in the cold trap condenser and officially condense the vapors, because dry ice has a temperature of approximately minus 85 degrees Celsius. Also, there's different applications that you can do with the condenser on a rotary evaporator. Let's say you're performing reflux reactions. You can actually get a condenser to do this on a rotary evaporator, work up your reaction, and then evaporate right into the receiving flask once you're done. You don't have to worry about sample transfer. You can also do Soxhlet extractions and also work with foamy samples on a benchtop rotary evaporator. So if you need high condenser flexibility, use a benchtop rotary evaporator. So here's a list of common applications for a benchtop evaporator. You can see the most common is evaporation of solvent after a chemical synthesis. So as a user, you work up your synthesis, your reaction, and then you have to strip off the solvent. This is mainly done on a benchtop rotary evaporator. If you're working with extraction samples or performing recrystallization, again, this is more on a benchtop rotary evaporator. Drying down powders is getting more popular because what's happening, you have your slurry mixture, and instead of putting them into a drying oven and letting it dry, you can put it into a rotary evaporator and really dry down the powder that much faster. And the last two are getting bigger and bigger in this field because the scientific industry is trying to go more green. So solvent purification and solvent recycling. What this allows you to do is actually recover your solvent. You can purify it. That way you don't keep using new solvent. You can reuse the solvent that you already used once, save money doing so, and you can actually save the environment by reusing the solvent and not just disposing of it. Okay, now let's get into industrial evaporation. An industrial evaporation is very similar to a benchtop rotary evaporator. In fact, all the parameters that apply to a benchtop rotary evaporator apply to an industrial evaporator. So let's say you already have your method development worked out on a benchtop rotary evaporator. You don't have to rework it on industrial. You can use the same exact method, the same exact parameters. You have your evaporating flask, receiving flask. The same. You have your primary condenser, vacuum pump, controller, and then also, if you notice, with this industrial evaporator, you have the chiller, which is actually in a compact trolley, so it's going to actually save space in a laboratory. And this is an all-in-one rotary evaporator. All the components that make up a rotary evaporator are controlled by that integrated vacuum controller. And like I said before, if you have the capability of doing this, work with an all-in-one rotary evaporator. It's much more efficient. So 3 main reasons why you would want to work with an industrial evaporator versus, let's say, a benchtop rotary evaporator is that you're working with larger sample volumes. Let's say you're working in a kilo laboratory or pilot plant. Usually you're working with 20-liter volumes. Production labs are usually working with 50-liter volumes. Well, an industrial evaporator can fit up to a 50-liter evaporating flask. Second reason, let's say your application requires high distillation capacity. An industrial evaporator is the way to go. I have 2 examples here shown with ethanol. You can see with a 20-liter flask, the industrial evaporator actually had a distillation rate of 13.5 liters per hour of ethanol versus a 50-liter flask, which had a 19.5 liters per hour. Now, it's the same instrument, same variables, and maybe you're wondering, why is that? Well, the fact is that the increase in the surface area in the evaporating flask is going to actually allow you to increase your throughput. It's going to provide a higher distillation capacity. And lastly, if you're working with some unique operation, let's say you want to perform a continuous evaporation process. You want to save money on labor and you don't want a user right there watching the instrument. You want to be able to hit start, go away. Well, the industrial evaporators actually have, not all of them, so make sure you do your homework, but some of them will have this continuous option where you can hit start and it'll actually perform the whole evaporation process until it's finished, and you don't have to be present. If you're working in an explosion-proof environment, EX-rated environment, well, there's industrial evaporators that are ATEX compliant. Also, very unique thing with industrial evaporators is that you can actually concentrate with some of them. Not all of them, so please do your homework. But for instance, the R220SE, you can actually concentrate to a residual volume with this, assuming you get the correct accessories. So if you're doing something unique like that on industrial evaporation, you can do so. So the most common applications with industrial evaporation is your first 2, solvent recycling, solvent upgrading. Those are your most common ones. Again, because the industry is trying to go greener, you can actually just reuse a solvent after you upgrade it or recycle it. Drying down powders, but in a larger form, a larger sample volume. If you're doing basic solvent evaporation, and then recrystallization, again, it's big with industrial evaporation as well, but obviously you're going to have a larger volume. Now let's get into parallel evaporation. The 2 technologies I have shown here are vortex evaporators. On the left, I have shown the multi-vapor, and on the right, I have shown the Syncor. These are 2 very common vortex evaporators. Very similar to benchtop or industrial evaporator, but they don't have the evaporating flask. The samples are actually held in parallel where you see the racks. You can hold those in parallel and evaporate multiple samples simultaneously. The vacuum covers what actually gives the vessels a seal, so you have adequate vacuum. With these vacuum covers, they're actually individually sealed vacuum covers because if anything goes wrong, you don't have to, with bumping or something on the lines of that, you don't have to worry about cross-contamination. So if you're in the market for a vortex parallel evaporator, make sure you do the research and make sure that the vacuum comes with individual seals on it. Because cross-contamination is always a concern with parallel evaporation as you're doing multiple samples simultaneously. And then you have your primary condenser, which allows you to actually collect the solvents and properly dispose of them, or you can actually recycle them, depending on how you want to adjust your workflow. Now, since I mentioned the multi-vapor and Syncor, I want to just give you the two differences just because, yes, they're both parallel evaporators, but they can do two different things. For instance, the multi-vapor has 6 or 12 positions, whereas the Syncor actually can have positions up to 96. Specifically, it has a 4, 6, 12, 24, 48, and 96 position rack. So your sample volumes are going to be a little higher on the Syncor as well. You can have a sample volume as high as 500 milliliters, whereas a multi-vapor, the max sample volume is 150 milliliters. The biggest difference between these two instruments is that the multi-vapor always goes to dryness. It's meant to go to dryness. Where the Syncor, you can actually go to dryness, or you could go to a residual volume. You can actually concentrate to a set volume, and we'll get into that next. Another unique thing with the Syncor is that you can actually do solid phase extraction on top of the Syncor, so you don't have to worry about sample transfer. You do your extraction, extract the sample into the vessels, and then concentrate it down. Also, there's an automatic rinse feature on the Syncor, which is known as a flushback module. This flushback module will rinse the sides of the glass vessels back into the chilled zone appendage, which I'm going to talk about, so you can actually increase your analyte yield. So Syncor, it's a little more, there's more options, more flexibility with the Syncor than the multi-vapor. So parallel evaporation, the three main reasons you want to go with this is if you're working with volumes of roughly 0.5 all the way to 500 milliliters. If you need high throughput, small sample volumes, then parallel evaporation is great. If you have multiple samples, let's say they're coming off a flash chromatography system and maybe you have 24 samples or 48 samples and you need to evaporate them all at the same time simultaneously, then you can just do it right onto the Syncor. Also, like I mentioned earlier, if you're concentrating small sample volumes, then go with the parallel evaporation unit, specifically the Syncor Analyst. It'll allow you to concentrate to a residual volume of 0.3, 1, or 3 milliliters. So this is that chilled appendage technology I mentioned. What you see here is a glass vessel with the appendage on the bottom of it. This appendage is actually in what we call the chilled zone, which can be a temperature of approximately 10 degrees Celsius. You can use a lower temperature, but I use about 10 degrees Celsius. And what happens is your compounds of interest that you need to take over to your analytical analysis, it's going to be chilled. So there's there's a very hard chance for you to lose these compounds. Everything outside of that appendage, which is in the heated zone, is actually going to be evaporated out. It doesn't rely on sensors because, as we know, sensors can fail. So we didn't want to use sensors. We wanted to use a different technology, and this technology is it's a very nice technology in the fact that it automates the process, and you don't have to be present when the evaporation is done. And you're very unlikely to actually go to dryness, to actually over-evaporate, because it's chemically proven that, let's say, if you're concentrating dichloromethane with a boiling point of 40 degrees Celsius, that it won't evaporate at, let's say, a chilled zone at 10 degrees Celsius. It's just not chemically proven, even if you reduce the pressure to a very low amount. So common parallel evaporation applications are stated here. I would say the biggest one would be the concentration of environmental samples. So if you're in environmental industry and you have, let's say, soil or water samples, you perform your extraction with, let's say, DCM, and it's about 80 milliliters of DCM, but you need to concentrate it to roughly 1 ml to take it to your analytical analysis. You would do it in parallel. You could do multiple ones at once, bring it down to a direct 1 milliliter residual volume, and then perform your analytical analysis. It's much easier doing it this because it's on a Syncor Analyst because it's automated and the fact that you can do up to 12 at once. Food feed analysis is another big application along with quality control. Chromatography samples, that's big as well. Like I said, let's say you have let's say 20 fractions that just came off your flash chromatography system. You need to dry all of them down. You might as well not put them in a rotary evaporator individually. It's best to do it in parallel on a vortex evaporator. Then extraction samples. This is also very common. You perform your extraction and you need to concentrate it down or even dry it down. You can do that on a parallel evaporator. Okay, at this point, I want to just jump into some polling questions to see how much you guys, the understanding of the presentation so far. So let's start off with the first question. You can start voting here. I'll give you guys a couple minutes to vote, but let's say the question is, when scaling up from a benchtop rotovapor to an industrial rotovapor, will the same parameters apply? A, yes, B, no. And I'll give you a couple minutes to actually to vote for this. Okay, very good. It looks like everybody's voting A, which is correct. The same parameters apply, so when you scale up, no problem. You don't have to redo your method development. The same exact variables will apply. Next question. What are the advantages of working with an all-in-one rotovapor? A, the evaporation process is more efficient. B, you consume less energy. C, there's higher automation. Or D, all of the above. And I'll give you guys a couple minutes for this. Okay, very good. It is all the above. Again, if you have the ability to work with an all-in-one rotovapor, do so. You're going to consume very little energy because the vacuum pump's controlled with the vacuum controller. It actually pumps it to your set vacuum and then pretty much shuts off that vacuum pump, and it'll fluctuate back and forth. Also, when you're controlling the chiller with the vacuum controller, if the chiller's not being used for about 5 minutes, it actually shuts off automatically. And as we all know that worked in a lab, leaving a chiller on all night has happened, so you don't have to worry about that with an all-in-one rotary evaporator. Next one is actually, what is the importance of evaporating under vacuum? A, evaporate at a lower, more gentle temperature. B, increase analyte yield. C, automate the process. D, all the above. Okay, so it looks like there's a little bit mixed from D and A. The correct answer is A. It's actually to evaporate at a lower, more gentle temperature. That's the most important factor that when you're utilizing a vacuum source. And now the last one. When is it advantageous to use a parallel evaporation technology? A, evaporate at a lower, more gentle temperature. B, increase analyte yield. C, automate the process. D, all the above. Okay, that was actually a trick. I just wanted to see if anybody was paying attention, but none of them are correct. It's advantageous to use a parallel evaporator when you're evaporating small sample volumes and you need a high throughput. So that's why you would choose parallel evaporation. Small sample volumes, but you need high sample throughput. All right, so that's it for the polling questions. Let's just summarize everything up here. So what I went over, always equate energy in to energy out. Make sure these two energy, remember the heat is the energy in, the coolant is the energy out. Make sure they're equal and attuned to one another so you have an efficient evaporation process. Always evaporate under vacuum. It's going to speed the evaporation process up, and it's going to let you use even more gentle temperature than what you would have to use if you didn't. When you're evaporating under vacuum, always utilize the change in 20 degrees Celsius rule. When you're performing parallel evaporation, or you want to perform parallel evaporation, the reason you want to do this is if you need high throughput of small sample volume. Benchtop rotary evaporators, the volumes are roughly 50 mLs to 5 liters. And remember, the working volume is a little different. The rule of thumb is half the maximum volume of the evaporating flask. So if you're using a 5-liter evaporating flask, you don't want to exceed more than 2.5 to 3 liter starting sample volume. In industrial evaporation, if you have volumes greater than 5 liters, then you're talking about industrial evaporation, and you would want to scale up at that point. Okay, so let's get to the questions here. Okay, so I got one. On an industrial scale, what is the best way to recover dried material from the flask when it has a thick paste consistency given the narrow neck size of most flasks? That's a great question. Okay, so your best bet, an industrial scale has a wider flange. I think it's 150 millimeters. So it's easier to get it out of an industrial flask than a benchtop flask. So you shouldn't have too much problems removing it from an industrial flask because that flange is pretty big. There are things called, we have a device called a suction outlet, it actually allows you to automatically remove the sample that's in the evaporating flask. That's for a 50-liter evaporating flask. But besides that, let's say the best way is to actually you would have to use a spackle and get it out that way. But our flasks do have a wider flange than most industrial evaporators, so you shouldn't have too much of a problem with a Buki evaporating flask. Now, if you're talking about a benchtop rotary evaporator, we have glassware known as beaker flask, where the flange is actually removable, and it's a big beaker, and you can put your hand right in and get it out more easily. Okay, next one. How do you fine-tune the vacuum to control the temperature of the vapor? All right, so this is a good one. So let's say, all right, let's go back to the water bath being 60 degrees Celsius. Let's say you're actually, you're pulling too aggressive a vacuum. What's going to happen? That vapor temperature is going to be higher. So it's probably going to be about, higher than 40 degrees Celsius. So let's say maybe it's 50, 60 degrees Celsius. Now, if you're not pulling aggressive enough vacuum, then it's going to be lower than that 40 degrees Celsius mark that you want. So you need to fine-tune it. Now, to actually get the measurement of the vapor temperature, what you need is a rotovapor that can actually that has a vapor temperature sensor in it. Our Buki R215 actually has this feature. So what you would do is just fine-tune it. If you see the vapor temperature is too high, you reduce the vacuum. If you see it's too low, then you increase the vacuum. Okay, next question. I have a Syncor analyst, and I want to use it as a Syncor evaporator. What do I do? That's interesting. So the Syncor is the actual platform. There's two configurations. You have the Syncor Analyst and you have the Syncor Polyvap. The Syncor Analyst will actually allow you to go to a concentrated residual volume, whereas the Syncor Polyvap will allow you to go to dryness. So if you're currently using the Syncor Analyst and you want to go to dryness, all you would simply have to do is switch out the rack and get a Syncor Polyvap rack. And then you would have the glassware that doesn't have the appendages on the bottom. The part numbers are all found in our literature, which is founded on our webpage. If you need additional help finding the part numbers, just give me an email and I can provide you with the part numbers and even get pricing for you. Is there any differences in evaporation throughput from a dry ice versus a water-cooled condenser? Not so much throughput. What can happen if you're using dry ice, since the temperature is minus 85 degrees Celsius, you can be a little more aggressive because your goal as a user is to keep that vapor level 3/4 of the way up the condenser. If you get it too far up the condenser, that's when you actually, like I said, you stack the condenser and pull solvent into the vacuum pump. So you're less inclined to actually pull vacuum in the vacuum pump because you're using such a low temperature. So you can be a little more aggressive with the vacuum. I don't know the difference, but how much of throughput it's going to help, but it would help on certain solvents. Let's say ether, DCM. I mean, those solvents are you want to use low boiling point solvents with dry ice. Just the fact that you have to worry about their volatility, how volatile they are, and the fact that they can re-evaporate from the receiving flask. So it's not so much the throughput. It's more the chances of the re-evaporation occurring from the receiving flask and keeping those vapors that are popping up back into the condenser in liquid form and dropping them back down in the receiving flask. Okay, next one. Do you have any performance data of your Rotavapor, lab and industrial scales, to separate butanol, acetone, and ethanol from fermentation media? Is it possible to sequentially separate butanol from acetone and from ethanol from a mixture of fermentation medium? I've heard of this application before, and yes, this is something that you can do, and I do have actual performance data on these solvents. So your best way, I don't have it on me now, but I'm going to get to the last slide, and actually you can actually just email me the actual solvents, and we'll get into that. I'll get you the actual distillation capacity and the throughput for it. Also, it looks like we're running out of time. I have a minute left here, so this is about it. If there's any questions I didn't get addressed here, please email me. Here's my contact information. I'll try to get the answer out to you as soon as possible. And then also, if you want a copy of these slides, that's fine. Just email me, and I can send you a PDF copy of the slides. So again, thank you everybody for joining today's webinar. I hope you found it beneficial. Have a good day, and take care. Bye.